Swayam Prabha. Digital India. Educated India.
Welcome back. We were discussing calculation of force or torque using the principles of magnetic energy and co-energy. If you recall, magnetic stored energy Wm or co-energy Wm dash. So, if you recall, Wm was defined as integral of EI dt, but in a single coil system EI is d lambda by dt I dt, or in other words it is I d lambda. So, in this system basically what happens is the state variable is lambda, the stored energy magnetic field energy is Wm, and we had taken a system in which, like a motor, we discussed some examples of relays and things like that. So, you have your electrical input coming in here. So, the voltage comes somewhere here, it pushes I. So, the electrical input comes here, and a kind of mechanical work gets done on the outside output sort of here, magnetic energy being somewhere the intervening medium here, and we had shown that Fe can be written as minus of with respect to delta x, the state variable, where this is now the magnetic energy is a function of x and state variable lambda. So, we said that we prefer most often we prefer current to be a state variable, and because we prefer current to be a state variable, we defined Wm dash as the as magnetic co-energy and that was for this single electrical source, single mechanical work done kind of a system, the basic relay that we discussed, for example. We defined this as this, that means the sum of energy and co-energy is product of lambda into I. So, we had a very simple example like this, where let us say this is the lambda, this is the I, and we have this lambda I kind of characteristic. Suppose you are reaching this state I naught, say lambda naught, then we had identified that this part is the Wm part, because it is lambda times of di. So, this is a strip lambda, and this is the I times of d lambda. So, this is my I, and then I take a small strip d lambda somewhere here, and I do this I d lambda. So, that is that I d lambda is exactly this small width. The basic current is I, d lambda is this small strip, I d lambda is this small strip, and then I am going to integrate it from 0 to lambda naught. So, I keep adding these strips here, here, and I get the W m. Now, lambda I product is this complete rectangle, lambda I product is this complete rectangle, and I subtract this from W m from here. I get what is known as the co-energy. So, this is my co-energy strip. So, this is with a kind of a single coil system and one mechanical work done and one coil which is pushing the electrical input source to magnetic field energy and pushing it here, and the other one doing the work. This is the kind of a system that we got, and in terms of co-energy, force can be written as W. So, you can see that this minus sign is already gone this side. So, it is co-energy is calculated with the state variables. Actually, if you just touch this point. So, dWm dash is d lambda I minus dWm, but this is I times of d lambda plus lambda times of di minus what is it that we had got for dm, something here you can see dm is I times of d lambda, I times of d lambda is dm. So, therefore, dWm I am sorry. So, therefore, it is I times of d lambda, I times of d lambda. So, therefore, this becomes the lambda di, and if so now what has happened is the state variable can be taken as di. This is the main advantage of working in the with the co-energy principle, that you can take state variable as this thing. So, for co-energy Wm dash, because it is also with machines or relays or actuators or things like that, it is also a function of x, and it is also a function of I, it is also a function of I. So, we had we can write this as dx plus Wm dash with respect to Wm dash with respect to di times of di, and actually when you are talking of machine, I mean this all my discussion that power input directly goes as magnetic field energy and so on is so long there is no mechanical work being done. If mechanical work is being done, then whatever incremental electrical power you push into the system, part of it will be stored as magnetic field energy. I mean, and we are considering it as a lossless system, conservative lossless, because losses we will always try to keep down to a small fraction through proper kind of mechanical engineering and so on. So, that small electrical energy which is being pushed into the system will go either as stored as a magnetic field energy, part of it, part of it will be used to do work. So this is under no moving parts, right. I mean in the electromechanical system, in the electromechanical path there is no moving path. But when there is a I am sorry, this dWm is going to be like this, but when there is a moving path, then you have you will have to write, if you look at this particular expression, let me correct this expression here, let me pick this. Copy somewhere here and so if you are looking at dWm dash dWm dash as d of lambda I minus of dWm, and dWm will be written as how will you write dWm as? dWm you will write it as EI dt, which is the electrical input, minus the FE dx, which is the part work which has been done. So, this becomes d lambda I minus I d lambda, because E will be substituted as d lambda by dt. So, dt and dt will go away. So, this will be left with I d lambda minus plus of FE dx, and so we expanded this can, when you expand this, I times of d lambda terms cancels out with I times of d lambda term here, and so you are left with lambda times of, so you are left with lambda times of di term here plus of Fe times of dx. Helps, these repetitions help, concepts we learn by repetition. There is a certain extent of repetition, but remember, second time I go much faster over it because you have heard it before. So now when I equate this with this, then I have to do the equating state variable to state variable. So, this one will get equated with this, and so I come to the conclusion that lambda will be partial derivative of this with respect to I, which means here the x is the partial derivative, means x is as if not a variable, x is as if it is a constant, because this is a function of x and I, and Fe will be equal to equating the dx and dx part here, Fe will be equal to plus of this thing, partial derivative with respect to x, partial derivative keeping I constant, So, I guess we are in sync with this, and remember, unlike magnetic energy, here it comes with a positive sign. So, before I take multiple energy, say 2 energy electrical energy, 1 electrical output, or multiple electrical energies and multiple mechanical output kind of a systems, both linear and rotational. Let me just take a simple example. let me work out a force calculation example. This is part 1, this is one part of the system, and this is the other part of my system. Okay. And I have a coil somewhere here, connecting a voltage, and let us say this side the mechanical system is represented by a spring and a damping spring with the spring constant K. I am not going to use that right now, and this damping of this. X is measured in this particular way. Let us say that, so this gap is x is measured like this is the x, this is the x, and let us, if you look at the flux lines path, it is going to be like this, and it does not matter whether the current is alternating or directional. Basically the action is that once you energize this, it is going to pull this side, and in the process you will do mechanical work because the spring will be elongated, and some working will get done in terms of this particular thing. So you are going to, your electrical energy will partly set up the magnetic field energy here, and partly will be used in doing the mechanical work. So let us find out the Fe, the force. This is the way H is going to be set up. Let us try to find out the force given that length in the core is Lc, mu is the mu r mu naught is the mu in the iron, and of course in air the permeability is going to be mu, area of cross section is A, everything being taken in meters, and we will treat this magnetic material as linear. So let us try to find out the co-energy, which what is our first task. So in finding the co-energy, the way we are going to proceed, remember I told you this one also, if you want the system, you want to calculate the co-energy at some distance x, you can first keep this unenergized and everything is set to 0, and you can just move one of them towards the other and bring it to the, for example, you can move this assembly towards this and bring it at the position x. So whichever position. So in moving this, either this moves later on or this moves, one of them moves, that effectively the distance here shrinks and so on. So in making that initial setup, no work is done because no force is required so long as no forces will come into picture so long as this part is de-energized, and I can just adjust my distance between this and these two part assemblies very easily. Once I have reached that, then after that I do not allow things to move, and that is to say that x is kept constant, physically means I do not allow things to move, and then energize this to the required current level di, or if I am calculating magnetic field energy, then the state variable is lambda, if I am looking at Wm dash, then I state variable is I, or the d or state variable is I, and I calculate this. So, lambda is I comma or I dash comma x d I dash, and I take it to this particular level. Now, how do I write lambda I dash of x? I can write it as Lx times of I dash. Anyway, it is a linear material, mu is constant, mu naught, mu r is constant. So, I need to calculate inductance. The inductance depends upon the reluctance of this path. Let us say this has n square turns here. So, then the inductance L of x will be n square by r of x, and this whole thing will therefore become inductance will become this, and once I know the inductance, once I know the inductance, I get the flux linkage, then that can be substituted here, and then it can be integrated with respect to I dash. So, the Wm dash is going to be equal to integration of 0 to I n square by r x, the inductance, times I dash the current, which is, this is the dummy variable used for current, because the limit of integration is taken here as I. So, therefore, the dummy variable used is I dash here, times of d I dash, which is n square by r of x, half of I square, which is half of n square by r x I square. So, I get this thing as my flux linkage, and Fe will be then partial derivative of this with respect to the state variable x, with respect to the distance state variable x. So, you have half of n square I square will remain, will be treated as if constant, and you are going to take partial derivative of 1 by r x, which is going to be minus of half of n square I square by r square of x times rate of change of reluctance with respect to x, unit being newtons. So, if you want to do that, now what is the only task that is left? The only task that is left is calculation of reluctance. So, in this thing, if you want to calculate the reluctance, you can write the equivalent magnetic circuit. So, the equivalent magnetic circuit is going to be this pushes Ni, and this part of core and this part of core, all having area of cross section A. Anyway, fringing and leakage flux has been ignored. So, it will give you a reluctance R c, which will come in series with this air gap resistance and reluctance and this air gap reluctance. So, equivalently, so 1 R g and the other R g. So, this becomes, and this is the phi. So, this becomes my equivalent magnetic circuit, and if I write for R g, then it is going to be 1 by mu 0 x by area of cross section, and if I write for the reluctance R c, it is 1 by 1 mu 0 mu r into L c by A. So, therefore, let us take this down and write everything properly. Let us pick it up from here and use this part here. So, the reluctance R is equal to R c plus 2 R g. So, therefore, you can take 1 by mu 0 A as common and 2 R x. So, 2 x to 2 R g. So, therefore, 2 x plus R c. So, therefore, L c by mu r, and I think this point I have been emphasizing again and again to all of you that L c is gets a length of the core, it shrinks effectively because of the mu r. So, like if mu r is 80,000, then and say this is say 10 centimeters, then 10 centimeters divided by 80,000, it is just equivalent of that small amount of air gap, but this will be already in say some mm's or some centimeters. So, this usually outweighs this quantity. So, therefore, as a idealization many times we take this component as 0. So, we got this now, we got this, and next task is, what is our next task? Our next task is to take the partial derivative of this with respect to x. In fact, directly we could have dr by dx, it would be more appropriate way of writing it. So, let me write this here as, because it only depends upon x. So, therefore, dr by dx is going to be equal to 2 by mu 0 A, because L c by mu r will not give me any component, right. So, with this if I substitute it here, and this is my F e. So, my F e turns out to be minus of half of n square I square divided by r square of x. So, therefore, if I substitute 1 by r square of this, so I will get 2 x plus L c by mu r whole square here, mu 0 square here, a square going up into dr by dx, and so the dr by dx is calculated as 2 by mu 0 a. So, I give it as 2 by mu 0 a, and so the f e turns out to be this 2 and this 2 cancels out, this mu 0 also cancels out. So, I get n square by minus comes out common, minus of n square by mu 0 a, n square I square mu 0 n square I square mu 0 dr by dx mu 0 a divided by, and minus of course divided by 2 x plus L c by mu r whole of square. So, this is what this is what I am going to get as in newtons, and minus because it I square is always positive, I am sorry. So, because I square is always positive. So, therefore, it shows it x is in this direction, Fe will be, if it is in this, it is a attractive force. So, therefore, the force is actually is going to be a attractive force. So, this is now what we need to do is this idea we need to take it further to two electrical and one mechanical port system. So, let us expand this. Finally, we are trying to go towards multi-port networks. So, as a next step, let us expand the idea of co-energy. See, 3-phase windings will have 3 at least multi-port system, even if the rotationally there is only 1 degree of freedom, actually there could be multiple also. But at least to begin with, we will have 1 degree of freedom on the mechanical, but electrical side many electrical sources will be there in a 3-phase system. So, we need to expand this concept of co-energy Fe for a 2 electrical at least. Next step is 2 electric, and then we will go to multiple also, and 1 mechanical port system. And incidentally, this thing is covered very well in the book by Fitzgerald Kingsley, as well as a book on electromechanical energy systems by Professor M.A. Pai. So, these are in my opinion 2 great references for this. I have mostly learned this story from their traditional other electrical machines book do a bit more empirical development of the treatment. So, if you have a system like this, then actually the lambda 1 strictly speaking will depend upon its current. Mutual coupling will be there because of there are 2 sources now on the magnetic system. Magnetic system is excited by 2 sources. So, I1, I2, and of course, it will also depend upon the couple X, which is the coupling between the 2. Similarly, the flux linkages which are associated with the second coil will also depend upon I1, I2 and X. So, this is what is Weber's or Weber turns, if you want to be more right, N phi, just reminding you, N phi Weber turns. And so, if you look at rate of change of the stored magnetic energy, that is going to be equal to the electrical power which you are pushing into it minus F into the velocity, the power output from the mechanical system. So, you need to look at the power output from the mechanical system, subtract that power from the electrical power input which is going into it, and that is the rate at which the the magnetic field energy is increasing in the system. So, I can write this as V1 can be written as I1 can be written as d lambda 1 by dt, V2 can be written as d lambda 2 by dt, and this can be written as dx by dt. So, if I multiply it by dt all over, I get I1 times of d lambda plus I2 times of d lambda 2 minus of Fe times of dx. And again we are following a motor convention kind of thing, that pump in electrical energy, get me mechanical work done out, and something in between goes as the stored energy in the this thing. So, I get I get this as this thing. So, but again, if I want to use current variables as my state variables, then I should change from Wm, that is energy, to Wm dash, that is the co-energy. So, I need to define now for this two electrical port, one mechanical output system, I should define my notion of co-energy. So, let me look at what d lambda, sorry, let me look at this see, in the single machine I said lambda I minus Wm. So, now I would be trying to sort of multi-port system, what I would be trying to do to define co-energy as lambda 1 I1 plus lambda 2 I2 minus Wm. That is the natural extension, right, and then later on we can scale it up to multi-port system or something like that. So, then this will be, if I expand this, it will be I1 d lambda 1 plus lambda 1 d I1 plus I2 d lambda 2 plus lambda 2 d I2. So, if I write this, so if I want to express this, which is I d lambda 1 plus I d lambda 2, I can write this as this minus subtraction of this, right. So, I1 d lambda 1 plus I2 d lambda 2, I am sorry. So, I am looking at this one is this, which is subtraction of this minus of this, and then substitute it here. So, I get, I am sorry, dWm as d times of lambda 1 I1 plus of lambda 2 I2 minus lambda 1 d I1 plus lambda 2 d I2 minus of Fe times of dx. So, now you can see that the state variables in terms of I1 and I2 have started coming in the system. See, lambda equal to L times of I. So, you cannot have both lambda and I as state variables, that does not make sense. Either you can have d lambda or you can have di, right. This is what is the idea, but the convenient one is the current as the state variable. Hence, instead of working with energy, work with co-energy, that is the idea. So, let us take, I am sorry, let us take this to this side and take these people to the right hand side. So, what I will get is d of lambda 1 I1 plus of lambda 2 I2 minus of Wm to be equal to lambda 1 d I1 plus lambda 2 d I2 plus Fe of dx. But then this is exactly what we should be, earlier we had defined this as the co-energy in the single port network. So, same concept translates here, and we define this as the co-energy Wm dash, which you get it as equal to lambda 1 d I1 plus lambda 2 d I2 plus Fe dx. Now, what are your state variables? I1, I2 and x. Earlier with magnetic energy you would have had it as lambda 1, lambda 2 and x. Now, instead of that we are having I1, I2 and x. So, we got this, and the same thing can be written as Wm dash if we want to So, now to calculate the Wm dash, I am sorry, 1 minute. Now, to calculate Wm dash, what we will do? We will integrate it. First, we will de-energize the system and bring it to the necessary x position. So, in doing that, this will not have any force, because if the system is de-energized, no Fe will be developed. Okay? The electromechanical force that we want, that is to be developed, that electromechanical force will not be developed. So, no Fe will be developed. Then once you have fixed the x, then at a time, first at that time I1 and I2 are both going to be 0, then increase the current I1 to its steady state value, whatever value you want, hold it there, then increase the current I2 from 0 to the appropriate value, and then that integration will give you the co-energy which is coming out from the system. So, what I am trying to say now is that you do first a integration from 0 to I1, whatever I1 you want, lambda 1, lambda was given as a function of what? This, I am sorry, this and this. So, I am going to increase I1 dash, I am going to keep I2 at 0, x already I have brought wherever mechanical position I want, I have already brought my system there, and then it is a path independent integral as we had discussed earlier. So, all that, please try to recall all that thing. Then now increase I2 dash from 0 to I2. At that point of time, the lambda 2 is going to be equal to, current is I1 is already sitting at I1, now you cannot change it, current has been in this state variable has reached. The way which you take to reach those final state variables is irrelevant in a conservative system. You can take any path, yet your calculation of energy and co-energy are going to be the same. So, our steps are first de-energize, bring x at the right level, taken care of, no electrical force was electromechanical force was created. So, Fe is 0. So, that part of the story is, this part of the story does not come into picture at all. Then when you are doing the integration, keep I2 to 0. So, this I2 being 0, this part will not have anything happening. So, increase first only I1 from 0 to I1 and bring it there, then do not change I1. So, this part of the story will not have any role to play in the integration. So, in the first path, this and this does not have any role to play, this never has any role to play because x is fixed, but in the first path these two do not have any role to play because I2 is kept at 0. So, dI2 is 0. So, only integration happens on the first part of it. Then when you take the path 2, which is that x is at the position, actually 3 paths, 0 to x reaching first its final value, I call it path 0. So, therefore, it does not worry me. Then I say path 1, which is I going from 0 to I1, and that will have a work which integration which will some integration which will happen here, but because I2 is fixed at 0, nothing will happen here. So, therefore, this term does not play any role. So, therefore, when I am integrating this only this on the path 1, only this, path 0 nothing, path 1 only first term comes into picture. Then in the second path, x is going to be at its whatever desired value, I1 is at whatever at its desired value, only current I2 is being increased from 0 to I2. So, therefore, this part of the integral will not play any role, only this part of the integral will play role. So, therefore, I have this second term. which is lambda 2, I 1 remains the same, I 2 dash increases from 0 to I 2 x times of d I 2 dash. So, this is how I calculate this is how I calculate my second term, which is associated with the second part here. dm dash, which is a function of I 1 sorry Wm dash, after doing that integral, two integrals, will be a function of I 1, I 2 and x. These integrals which I showed you here, I am sorry, these integrals which I am sorry, these integrals which I showed you here, after I have done that, it is going to be a function of Wm dash is going to be a function of I 1, I 2 of and x, and that if I am looking at the dWm dash, then I can write it as dWm dash partial derivative with I 1 times of d I 1 plus dWm dash partial derivative with respect to I 2 times of d I 2 plus Fe times of dx, and sorry, what am I doing, plus dm partial derivative of x times of dx. And then when I equate this to this, I get lambda 1 as this partial derivative, lambda 2 as equating this to this state variable by state variable by, and most importantly Fe equating the dx state variable here with the dx state variable here, positive rate of change of co-energy with respect to x, which is exactly the same expression as I had got it in case of the single system, single this thing. So, only here the difference is, earlier this was only a function of I and x, now this is a function of I 1, I 2 and x, that is all, but other than that it is same.